Get started. So, welcome to the second installment of our James seminar series. We're very pleased to have Jack talking to us today about low-rank approximations for kinetic models. Jack.
Thank you. Thanks everybody for attending my talk. As everyone said, I'm going to be talking about asymptotic-preserving dynamical low-rank approximations to the Vlasov-Fokker-Planck system. So a lot of those words are probably familiar, but I'm going to explain every single one. So let's get started. All right, so first I'm going to be talking about just an intro to kinetic equations of plasmas. I'm not sure how many of you here are attending the kinetic workshop versus the others, but discuss the master equation a little bit. And then some numerical challenges associated with solving it computationally. Then I'm going to discuss a technique known as dynamical low-rank approximation, which is relatively new and has sort of started to be used for kinetic theory more recently. And then discuss an asymptotic-preserving variation of that and apply it to a sort of model equation for plasma kinetic theory. And then finally, I'll talk about some challenges that still remain and future work that can address those. All right, so here's our first slide. As I said, we've got a big master equation for plasma kinetics. So the first two terms are simply a transport term. This third term is our Lorentz force term, and we've included the V cross B term for the magnetic field. And then we've also got collisions on the right-hand side. And so I'm calling this a Vlasov-Fokker-Planck system because I'm mostly interested in the cases when C takes a Fokker-Planck sort of form. So by that I mean this sort of diffusion and drift operator. And there's many models that are possible of these two factors, the drift and diffusion coefficients. Classically, there's this Rosenbluth potential formulation, which is actually equivalent to the Landau integral differential operator. And you can find these potentials by solving inverting a Poisson operator. More simply, you can consider like a single species case. This has been called the Doherty-Fokker-Planck operator, where here I've got an isotropic diffusion and a drift, and the coefficients here are just determined from the moments of f, so the second and first moments of f, respectively. So just as in sort of neutral fluids, there are many asymptotic limits that can help us solve these equations more effectively. So I'm just going to throw this normalization up here on the screen, and there's a lot of physical constants here, but out pop if you do this and introduce sort of your characteristic time scale, tau, and a length scale. It reveals these sort of three natural frequencies of the plasma dynamics. So the first is this omega p, which stands for the plasma, the proton plasma frequency. And that's basically the frequency of a natural harmonic oscillator under these electrostatic forces that are present. Next, you've got the omega c, the cyclotron frequency. And that's the frequency of gyration of a single charged particle around a magnetic field line, right? So that the magnetic force is perpendicular to the velocity, and you get these orbits. And then finally, nu p tau is nu p is the characteristic proton collision frequency, and that sort of scales with the temperature and the density. So together these tell you like what's the effect that's strongest in my plasma. Right? When the plasma frequency is very large, you'd have no charge separation. There's no chance for electric fields to form, really. When the cyclotron frequency is very large, it's very magnetized plasma. And then the most important one, sort of for coming up with nice models, is this nu p tau, which takes the role of the inverse Knudsen number. So when this is very large, you are in your hydrodynamic limit, right? And again, just as in neutral fluids, you can derive nice equations that are posed in only the three spatial dimensions for the evolution of the moment of f. So this is a big savings, right? We started with a 6-dimensional equation, 3 in physical space, 3 in velocity space. and we're down to 3. So that's great. If we're in one of these regimes, we're probably going to use a fluid model to solve our dynamics. Sort of interesting and special to plasmas is this case where you're strongly magnetized, and there you can actually average over a single orbit of the cyclotron motion. And so that lets you reduce the dimensionality by 1. And that's pretty widely used for magnetic confinement devices. And then, of course, in the absence of any of these sort of simplifying limits, you still have to solve the full equation, right? The full 6-dimensional kinetic equation here. So a natural question to ask is, are there any sort of off-the-wall numerical techniques that we can apply to reduce the computational dimension of our problem and save some work? So we draw a lesson from the science of large data matrices, right, of big data. And the idea is, well, almost all huge matrices are actually extremely rank efficient, right, in a numerical sense. So what do I mean by that? Well, I mean that a truncated singular value decomposition is actually a good approximation to your matrix. So let's let A be an m by n matrix, and m and n are written in capitals to remind you that they're very big. So A has got a singular value decomposition, use sigma v transpose. And what we can do is basically pick a cutoff R, and we're just going to drop the first, or everything past the first R singular values. And if we have this smallness, where if the rth singular value is very small compared to the first, then this truncation is a very good approximation to A. So this is a pretty standard idea in intro numerical analysis courses. But the point here is that this truncated SVD representation requires way less storage, right? If m and n are very large and r is much smaller, then we're down to r times m plus n, which is going to be way smaller than the product, right? So you can save a lot of storage using this truncated SVD type representation. Okay, but let's see. So yeah, so is there any reason to believe that this is going to be helpful for these kinetic equations of plasmas or just any kinetic equation? So this is an example due to Lucas Einkammer, I think. And basically the idea is, let's say I've got this initial condition where it's a Maxwellian, but it's got a sinusoidally varying density in space. And I'm going to evolve it under this super nice linear transport equation. And oh, lo and behold, it ends up looking like this, right? You get this filamentation of the space-based distribution. And so if you're applying some classical discretization to this, let's say it's spectral in velocity, this is really bad news for you, right? The Sobolev norm in the velocity direction is increasing exponentially. And so there's this difficulty that's well known about kinetic equations in general. You get this problem. So we have this nice coincidence, though, that at least for this sort of very carefully chosen initial condition and equation, you can represent it as the sum of two functions which are exactly separable in x and v, right? X, v. That is, they're the product of some function that depends only on x and a function that depends only on v. And there's only two of them. So if we had, if we're trying to represent this function, we can do it in much less space than the full phase space tensor product matrix requires. All right, so that sounds nice, but it's not going to do me any good unless I can handle time as well, because we've got these time-dependent problems. And so what we need to do is somehow be able to step our solution f in this low-rank form, right? We want to evolve it without having to generate the full phase-space distribution and then crunch it back down to Fres form every time. So in order to do that, we're going to employ this dynamical low-rank approximation. A brief history about that. I think it actually has a longer history than this, but it was sort of analyzed in 2007. I say proposed, but I'm not sure that's right. in 2007 for these sort of matrix valued ODEs, right? You've got some big matrix, it's got a time derivative. How can I solve that in a low rank form? Then it's been extended to this higher order tensor low rank decompositions. So I've got like a 4D of fourth order tensor. You can apply the same ideas and get even more savings. And then sort of the thing that made it possible to apply this practically for a time-dependent problem has really been the development of these over-approximation insensitive integrators. So what I mean by that is you never have to invert the matrix of singular values S. And that's really nice because if you're doing well, if your low rank approximation is good, then S is going to be super, super ill-conditioned, right? The smallest singular value should be really small. So this is key. And then sort of more recently, it's been applied to kinetic equations. So I'm going to talk about that. So let's consider some arbitrary equation of kinetic type, right? It depends on x and v, and it's just got some right-hand side h, so some time derivative h. What we do is we look for approximate solutions of this form, where f can be written as the sum of up to r squared functions that are xv separable. And some notation, the integer r is the rank, and these bases x and v are orthonormal, right? So we have these orthogonality conditions. This is pretty similar to the SVD so far, except that we don't require that S be diagonal. So the x and v are allowed to interact not just in a diagonal way, which means that this decomposition is not unique, right? So that's fine though, because what makes it dynamical is that we don't necessarily need a unique decomposition of f. We're going to decompose the time derivative of f. And we do that by imposing a Galerkin condition on that time derivative h. So in this schematic, this manifold MR is simply the manifold of all the functions that you can write this way, right? And at each time step, we're going to take the time derivative that our system wants to follow and basically project it onto the tangent space of that manifold. And so, of course, as you send delta t to 0, you're going to be stepping along the tangent space, which means you're stepping along the manifold. You're following a trajectory in this low rank manifold. Okay, so it's a projection, like I said, and you can write an explicit form for what that projection is. And it turns out to have this form, where right here, where you can write it as the sum of a projection onto the x space, projection onto the v space, and then subtract the projection onto both spaces. And this lends itself to a really nice first order in time operator splitting. You just look at it and you're like, okay, I'm going to do this part, and then this part. So that's what we do. You evaluate along the v direction, and then the x direction, and then in the middle you go backwards a little bit. So, and these steps can be sort of reordered as well. Let's see. So just quickly to let's see if we've gained anything here. Well, this problem I've integrated over v, right? And I'm doing this for each basis function in v. So there's r of these equations to solve. But since I integrated over v, this equation, each one is only of size nx. So it's much smaller than nx times nv, right? Similarly here, I've integrated out the x dependence, and there's still r of those. So the cost of this should be like r times nx. This middle one is the smallest one. There's just r squared equations. It's like an ODE. All right. So pros and cons, we just did this sort of back of the envelope calculation, and we convinced ourselves that this approach should be really cheap, right? Compared to solving this full kinetic equation, it should be much smaller. It should be, basically, we achieve the full cost savings that was suggested by this truncated SVD idea. But does it preserve the structure of the equation, right? So all of these kinetic equations have really nice structure that we know from theory. They the entropy decreases, they tend to a Maxwellian, and they conserve various quantities. So importantly, is it conservative? No, it's not. Unless you do something special to make it conservative, what happens is these conserved quantities sort of leak into the range that you're truncating at each step, right? You can imagine that if the function v squared is not exactly representable in the v basis, it's not in the span of your vj, then you're going to be failing to conserve energy. So you can sort of get around this, and there's a reference here about that, which is interesting work. The next one is this Maxwellian asymptotic limit, right? So do we approach the Maxwellian, or is our scheme behaving nicely with respect to this limit? And the problem there is that the Maxwellian with spatially varying parameters is not a lowering function. It's not separable. It's not even close to separable in x and v. And so you, what that means is that this scheme, as I've sort of presented it, when you're getting near the Maxwellian, you're doing just as much work, more or less, as you are far from the Maxwellian, right? And that seems wrong. It's not fair, because there's all this structure that we know about in the solution, so we should be able to exploit that somehow, right? We're leaving structure on the table, unless we can approach a Maxwellian without requiring a bunch of ranks to represent it. All right. So now I'm going to talk about one way to address that problem, the Maxwellian asymptote. All right. So in this work, we considered this simple sort of test case problem, and this has been called the high field limit of the Vlasov-Fokker-Planck equation. So this is a linear Fokker-Planck operator, and we call it Ampere because this is Ampere's law. So this is electrostatic, right? And then importantly, the electric field and the collisions have the same scaling. And let's see. So physically, you can imagine this is just one species, right? But it can have a background charge density, and so you could maybe think of it as like a fluid of electrons moving at high frequency, but against like a static background of ions. And so since the mass ratio of those two is so high, often that's a pretty physical approximation to consider. I believe it's also been used in the semiconductor application. Anyway, so what's the limiting distribution of this, right? Because our whole aim is to also capture a limiting Maxwellian in this low X scheme. So what's the limit? Well, it's this. We introduce this local Maxwellian, which has a flow velocity E and is isothermal. And there's also no density factored into here. That's going to be somewhere else. So once we introduce this M, our Vlasov-Fokker-Planck equation can be rewritten in this way. And so I won't labor the point, but you can convince yourself that as epsilon goes to 0, this F naught should approach M times some function depending on X. And this is the function that we'll call rho, the density. And it's going to be equal to the 0th moment of F, so just by construction. So this rho that we just wrote down also has a limiting fluid system. And it's not a super interesting one, but we can discover it by taking moments of the equation and sending epsilon to 0 again. And we find that rho E ought to equal J, which gives us this coupled system here. So Ampere's law again. And this is like a continuity equation for rho, right, with velocity E. And it sort of describes like a creeping flow of charge to neutralize the potential gradient. Let's see, so we've got these two systems. What do we mean by asymptotic preserving exactly? Well, let's suppose we write down this continuous kinetic equation. And we also have this continuous fluid equation, right? So if we have dynamics for rho, we can imagine projecting a Maxwellian out into phase space with that rho. And so the C fluid is going to be like the system that describes the motion of that Maxwellian, which is creeping along to neutralize the potential. And both are coupled with Ampere's law. So what we look for is this kinetic discretization, D kinetic, which is consistent. It's consistent discretization of C kinetic. So here we might have to send R to infinity, right? If the solutions of this get too complicated, we might need a really high rank to capture those. On the other hand, as we send epsilon to 0, this D kinetic should converge to a continuous discretization of D fluid. And the idea is that this bottom path needs to hold without sending R to infinity, right? So earlier I was saying that the Maxwellian is not a lowering function. And so without any trick, we're going to have a problem achieving this convergence for sort of some small r, right? So what do? Well, we, instead of evolving f in the low rank form, we're going to evolve g, and we define this auxiliary function g to be f divided by m. So if this is the limit of f, rho times the Maxwellian, our g approaches rho, right? And this is clearly rank 1 in x and v. It's a separable function of x and v. All right. So this has some hope of being low rank in the limit. So that's what we're going to evolve in the low rank form. All right. So this is our ansatz once again, and we can plug this f equals gm into our equation and derive this right hand side h, which is the thing that we're going to project onto the low rank manifold. So to achieve this, we introduce these auxiliary bases k and l. And we sort of identify these with, we identify their time derivative with the part that appears here in the projector-splitting integrator, and then take it one by one. So the first step is the k step, and I just kind of skip over these, but you can see what we're doing is projecting, we're taking the, taking the inner product of the time derivative with Vj, and expanding it all out. And then we advance Kn to Kn plus 1 via this. So you can use any order and time scheme that you want. And we end up using a first order IMAX scheme. So after that, you perform a QR decomposition. So what we've got here is like this Kn is x times s. And so it contains the basis, and it also contains the matrix of singular values. So what we can do is take this k and do a QR decomposition to get the new orthogonal basis for x. So that's what we're doing here, and we're given some intermediate s prime, and then we advance that and do the same with our L basis. So now by the end here, I've got a new xn plus 1, a vn plus 1, and sn plus 1. And so as you can see, this technique is really like finding its own basis, right? You advance these auxiliary bases, and then you pull out the information that represents the span of that new basis. So let's see quickly about the discretization. We're using a second order scheme, second order finite difference in v and x. The v part, as you can see, is it's not a good example, is somehow diffusive, right? The x part is hyperbolic, so this part. So we use a central scheme for v and a flux limiter for x. And as I said, we use this first order in time IMAX scheme to handle the coupled advection diffusion parts. So to make that clear, this is doing some, that's not a good example. The k is doing some advection. This is doing some diffusion. So we treat this part implicitly and this part explicitly. And briefly, I'll note that you have to be a little bit careful with this ill-posed ODE. So if this is diffusive, well, S is running it backwards, right? So this is like a reverse heat equation, which is very bad. But if you're careful about the time discretization that you use to solve this, it turns out to be fine. Just doing it for one time step, right? Because it's like just a correction. Okay, so some numerical results. I said that the small epsilon dynamics should be captured with very few ranks. So here we see that it does pretty well at rank 4, and it's sort of already saturating rank convergence. If we went much higher, it wouldn't be better. On the other hand, in this kinetic regime, so this is epsilon 10 to the minus 6, this is epsilon 1. So in this kinetic regime, we see this is starting to do this filamentation thing, and we do indeed require a higher rank, right? So at rank 20, solution looks pretty good, but at rank 12, there's this sort of interesting looking error that somehow, due to the bases not properly capturing the solution. So a 2D example, we can reproduce these dynamics through like a range of different regimes, right? So this is epsilon is 1 over 100. This is epsilon equal 1. And our initial condition is this like Gaussian pulse moving this way. And the white region is like a potential hill, right? So it is a void in the background density, meaning that there's like a negative potential there, and the electrons should struggle to get through it, right? In the creeping flow fluid regime, they won't move through that at all because they have no inertia to get them over the hill. But in the kinetic regime, they manage to, and you can see that it's retained its momentum basically through that point. So and then on this side, you can see that it's avoiding the potential hill. So we also managed to verify the performance gains. This is kind of a big table, but the thing to pay attention to is these bolded numbers, which are the empirical exponent of n. So each one is n by n by n by n domain. And we see that this low rank form is basically getting n squared performance, right? Or it's linear in the number of degrees of freedom in the x direction, y direction, for a fixed rank. And the rank scaling is like linear in the rank, pretty much. On the other hand, this full tensor solution is seeing n to the 4th performance and much higher memory usage. Right. Okay, so a brief note on some of the challenges that you still arise when you're trying to do this kind of thing. So even though we're able to capture this asymptotic limit, there's still a bit of a challenge with like the structure preserving question, right? So in not the low rank version, but you still divide by m, and then you've got this collision operator, which looks like this, and it's very well behaved. You can show that like the kernel of this guy is just constant functions in V, which is what you want, right? You want your thing to be sending you to a Maxwellian, which means a constant G in velocity. But when you project this onto the low rank basis, it turns into this hairy matrix where the diagonal entries are like this, but centered around a different flow velocity. So EK is like EIK is this integral. And then the off diagonal entries are like this cross advection thing. So it's unclear how to prove that the kernel of this guy is constant functions in V. And yeah, so the problem that arises, I think, is like this collision operator, your M is really combining X and V in a super not separable way. And so when it appears inside the collision operator, then projecting that, you're sort of destroying any structure that you were able to show about it. And then second, so an aspect of this scheme is that you have to compute a projection of the Maxwellian onto your basis. So for example, in this one, your current density J is defined this way. And so this is like a first moment of F basically, but F represented in the low rank form. And it costs nx times nv to compute this integral. So it's this. Luckily, by design, it's an isothermal Maxwellian, and so you can use this convolutional structure to compute it fast. But in general, for non-isothermal equilibrium distributions, you're going to have to sort of figure out a way to deal with this and accelerate this computation. We suspect that it can be done maybe somewhat nicely, since there is still so much structure in the Maxwellian, right? There's exactly like nx information in it. So I'm optimistic that this can be overcome. And then I'll just quickly touch on a couple of extensions of this idea. So rank adaptivity, I didn't mention this, but it's possible to monitor this diagnostic that you have just built into the scheme of the ratio of the smallest to the first singular value. And if that gets too big, then your basis might need extra functions, extra space to represent the solution properly. And so in that case, you can basically just add a random basis function, and the scheme will like figure it out. We'll figure out what to do with that extra space. On the other hand, we've got these order 4 tensors, as I mentioned. So you can do this tensor decomposition idea and get even better performance. So yeah, so this idea applies maybe especially well to kinetic equations, where, for example, the Maxwellian is like going to be separable in V and V2. So there's probably extra opportunity to employ it there. Let's see. So just in conclusion, we think that this low rank method is a pretty promising approach to really accelerate the solution of kinetic equations. And you've got to be careful though, right? Jingwei likes to say that it's sort of like a sledgehammer, right? You just shove everything into this low rank form, and you've sort of forgotten all the structure of the equation along the way. But I think we're showing that it's possible to recover some of that structure as long as you're careful and analytical about how you construct the scheme. So yeah, that's my talk. Any questions? Mm-hmm.
Is there any principle for choosing these xi's and vi's, the singular value decomposition?
Is there any principle
For choosing these guys?
Yeah. No, not really. It's just it's really just done by a singular value decomposition. So to initialize it, what we're doing is taking the initial f and then constructing the full tensor version of that, and then doing an SVD to get the basis functions. Yeah.
So once you have this SVD, I couldn't figure it out. At what point you introduce Galerkin projection? So could you please talk about it?
Yeah. So we have this. It doesn't come in at this point, right? It comes in when you have the time derivative of your equation. So here, this is the h that we're going to project into this tangent space. And I wrote down the form that the projector takes, and it's this, right? So the projection happens at the level of the time derivative, and then by taking steps only in this tangent space, you can stay along, close to the manifold.
What is h in here? That's my other question.
Yeah, sorry. H is the time derivative.
Okay, h is the time derivative, and you're taking a Galerkin projection of the time derivative.
Yeah.
Okay. So if I do that, then all right. So this is analogous to something I would do with spectral methods as well, right? I would take a Galerkin projection of the whole equation, and then I have some coefficients that I march in time, right?
Yeah.
So that's very analogous with it.
Yeah, I think that's a fair analogy.
Okay, so the part I'm trying to figure it out, how do you combine those kind of ideas and you combine SVD? Are you trying to say that the basis that you're trying to project on are actually from your SVDs rather than using some sort of orthogonal polynomial. Is that correct?
Yeah, that's right.
Okay.
So yeah, you do require that the basis functions be orthogonal, but you're not just projecting, because you can imagine taking some arbitrary orthogonal basis and then doing a Galerkin projection onto that. But what we're really doing is doing a
Find the orthogonal projection from the SVD. Find the orthogonal polynomial from the SVD, right?
So we do that, and then that's your initial basis, and then church don't want to go. It's fine. That's your initial basis, and then but what we're really doing is taking the projection onto this tangent space, and the tangent space isn't the span of one of the bases or the other. It's the tangent space to this manifold of functions which can be written this way, right? So I haven't included like the derivations of this, but the Galerkin condition is supposed to apply for all functions in the tangent space of this, and you can write down an expression for what an arbitrary function in that tangent space is, and then you test against that to get your conditions. And so we do you do that analysis, right? But then you sort of set it aside because you can show that the projection that you just performed has this form, and so this is the one that we actually use.
Okay, I'm trying to figure it out. How do you arrive to this form? But there must be a formalism for it. But if I have to start with it, that F over there, can you go a slide back? So one more slide back where you have the F. Those are your bases, right? In your initial basis, or is it Vj which is the initial basis?
Vj and xi are both the initial basis.
Okay, that came out from your SVD.
Yeah.
Okay, and if you compute this sum, then F is just your original data. That F cap over there, F data.
Whoops.
Yeah, it better would be to use it.
Oh no.
We'll come back. Yeah.
Okay. So we have this, right? And this is, so the manifold is functions that can be written this way, and the tangent space is something like delta x and what's some delta f of j plus delta vj, right? So the tangent space contains functions that, change a little bit, where you change the x basis a little bit, and the v basis a little bit, and you can change the s matrix a little bit. So does that make sense?
Yes.
So you're really not doing a Galerkin projection onto either of these bases.
Okay.
You're doing a Galerkin projection onto functions like this.
Okay.
Yeah.
Okay. So right. So what's the okay? So you're now going to be taking H, the Galerkin projection with that delta F bar. Is that okay?
Yeah.
Okay. And okay, with some linear algebra, you arrive with that form that you showed
For the
me.
projection.
All right.
Right.
So I'm in the next step. I'm now trying to do time marching, and so f prime is the time derivative, and I see that f double prime there is.
Sorry, wait, this is not the time derivative. This is like an intermediate value.
Okay.
Yeah.
I see. So it's sort of a splitting scheme.
Mhm.
Okay.
Yeah, exactly.
So
So this is the first order version of the splitting scheme that you can imagine doing a higher order
okay.
operator splitting.
Okay. Okay. I guess that solves all my questions. Thank you.
Yeah, thank you.
So you have you were saying some of the cons of using the low rank stuff. So Ampere was nothing low rank, they're not solving. And then the other thing was the
conservation.
So
Yeah.
does this take care of those, or is it
No.
needed to adapt it?
I don't think that, so certainly this doesn't do anything special to ensure conservation. You could, I guess, imagine doing some adaptive thing to help you with conservation, but it wouldn't be exact. I'm really just speculating. But in order to do the conservation, what the paper that I reference does is basically force 3 functions to be in the basis Vj, and to be in that span. And so you need to do some extra work around at this point of the derivation to make that work. And you can't use this projector splitting. So there's it's definitely an interesting paper. But I think that's the state of the art in terms of ensuring conservation for these methods.
A little new to kinetic theory, if I may ask a little trivial question. So F in here is the density, is it? The original equation that had F, which is the density, right?
F is the phase space density.
Okay.
Yeah.
So from that, if I want to compute my pointwise velocity, how do I do it?
Yeah, you take the first moment of F. So this.
Okay,
So yeah, the interval of F times V.
I see. And generally, you will create a sort of a lattice where you will have an up velocity, a down velocity, like something like D2, like Q13 or something like that. Or are those velocity models?
I'm not sure I understand the question. Do you mean
Lattices maybe?
so we do a finite difference discretization of this, but the unknown that's defined at each grid point is F.
Okay.
And so this is V, and this is the X direction.
I see.
Yeah. And then F is co-located in these.
Okay. Now since I have now I have F at every nodal value, I can compute U at every nodal value.
Yes. Yeah. So then the U's will be defined
Okay.
one-dimensional. Yes.
Okay. Little more trivial question, if I may. If I want to describe the plasma with let's say with Navier-Stokes equation and with some additional terms with magnetic field and everything, my motivation would be that it is a much simpler description for me to describe plasma turbulence. But now I would understand what there must be some complication involved with it, and if you want to give a 2-minute brief.
Sure. I think that there's a bunch of reduced models for plasmas, and the one that I think people use for describing turbulence is actually called MHD, magnetohydrodynamics. And the difference there is that you assume that there's never any charge separation at all. So you send the speed of light to infinity, and like formally that means that you're dealing with one fluid, basically. Even though you know that at root there's 2. And so that's a sort of a further simplification that people use. And as far as the more straightforward version of the derivation, you can do a 2-fluid model, which does look more like Navier-Stokes, right? Where you can do an ideal 2-fluid, which looks like Euler. Various things are definitely possible. But as far as I know, I think the turbulence people use MHD.
Okay.
Yeah.
And can you also talk about turbulence in your kinetic theory description? Possible to include
This one has no turbulence.
Okay. But is it possible to have additional terms to account for it?
Let's see. I don't know about. So you're asking is there?
I'll add 1 or 2 terms, and or maybe if there is some modification I can do.
Yeah. To what equation?
I
we add
wouldn't
the
know
term.
much, I
Yeah.
wouldn't know much about it, it's your subject area. I'm trying to learn.
I'll say the
from you.
same.
I don't think so. I think the scale. Kinetic the motion is very, very stochastic, very chaotic. There's no distinguish between both turbulence and kinetics.
Yeah, I get that, but I was thinking of, I can still simulate it by complicating the collision operator. Is that possible?
To simulate it by complicating the collision operator
Yeah.
to possibly add a term there to account for turbulence. I suppose what you do see in this, in like the Vlasov-Poisson system, for example, is phase-space turbulence, where you do get like electron trapping, particle trapping in these phase-space potential wells. So that's certainly very turbulent, but I don't know if I don't think that's really what you're driving at.
You're the expert. I was just trying to learn things from you.
Oh, thank you.
Thank you anyway. It was nice discussion for me.
Thanks.
Okay, and that was a question. Since
Yeah.
we're actually not good. What's the scale of fluid compared to speed of 20?
Newton number compared to the speed of light.
Yeah, which one is, so when we take asymptotic limit,
Yeah.
does it make sense to converge to Fourier equation first and then take the speed of light to infinity, or is the other way?
The hierarchy that people usually sort of throw around is kinetic model to the two fluid model, which allows charge separation.
Yes.
And then from there to MHD.
Yes, this.
Yeah.
That doesn't make sense. These are two parameters.
Right.
So which one goes to the limit faster than the other?
Mhm.
To detect it when you should take the limit.
Right.
Which limit? So do you know the scale?
What's the scale of applicability of that assumption?
Yeah, just which one is
Right.
dominant? Like which one go to the limit first and then to the others?
Well, there's such a wide variety of regimes
Yes.
that we could be talking about, that I guess it's really hard for me to answer that question.
It's okay.
So no, it's fine. So I'll just say like MHD, right? Which is you think is like this ultimate fluid model,
Yes.
is used to describe astrophysical plasmas, where there's no collisions happening, right? There's like 6 particles per cubic centimeter, but it's still useful there because the length scales are so large that basically the charge separation doesn't become an issue.
Now that could be happening because interchangeability. You are the same as it could be done possibly.
Yeah. You're right.
In reality, I hope which one is complex.
Well, like I say, I think it depends. It depends too much on the parameters that you're trying to operate within, because the collision frequency depends on temperature and density. So
Okay.
I think you get different answers in different
Kind of.
regimes. Yeah,
Thank you.
it's a good question.
Any more questions? Jack? All right, well, thanks again for the very nice talk.